Hi, and welcome to this video about interactions, or in the short form we could say Newton's third law. A couple things to think about. First of all, our definition. Forces are an interaction, or a force is an interaction between two objects that looks like a push or a pull. Here's our first example. It says a hand pushes a box that pushes a box, as in the diagram below. Now, I'm going to call maybe the first one here box number 1, and the second one box number 2, just so it's easier to talk about. I think your photocopy, it's not blue and yellow. If I said blue and yellow, it might be kind of difficult. Is there friction or not? Let's go ahead and say, yes, there's friction when we're thinking about this one. And we're going to think about how the forces interact between the two. So we have a hand pushing on box 1, but now let's think about how box 1 and box 2 interact. So there's going to be, I don't know, if we draw, here's box 1, and here's box 2. We're going to, how would we say that if we draw the force diagram for box 1, we want to draw the forces that are acting on box 1. So which way is box 2 pushing on box 1? To the left. And what kind of force would we call that? It's between these two surfaces, so it's a contact force. I think the best way to describe it would say it's a normal force. It's going to be a normal force on box 1 by box 2. Now how about box 2? That one's a little bit easier to think of, that one is pushing it to the right. So in this case, there we are, this normal force on box 2 by box 1. And so in our classic definition here, we're going to say that these two forces, they're equal and they're just the opposite direction. So really that interaction is just the force in between those two. It's the same force, just when we look at it acting on box 1, it's to the left. When we look at it acting to box 2, it's to the right. Okay, so let's take a look then maybe at trying to do the whole thing. So we just did one force acting. Clearly there's more forces. Before we're going to get right into it, I'm going to introduce the idea of a schema. Which is a really fancy word here, but it means kind of like an overall plan, overall picture, overall model. I think it's a Greek word. It sounds kind of cool, so let's use it, schema. So what we're going to do is we're going to think about all the objects that are involved in this situation. So I got a hand. Think of the hand as an object. I've got box 1. I've got box 2. I got a table. Maybe I'll draw the table over here. We don't have to draw them, oriented according to where they are in space. We can draw them anywhere, but sometimes it's easier to draw them like that. We also have the Earth, because the Earth is involved with the force of gravity here, and I'm going to put the Earth up here so I don't have as many lines that are crossed. Now, let's draw lines for when there's an interaction, a force between the two. So the quickest one people like to talk about when we draw force diagrams is the force of gravity, and that's really an interaction between the Earth and the object. So we would definitely have this one here, we'd have that one there. I guess the force of gravity would be acting on the hand too, and the Earth and the table, and we would have all those lines. Is there an interaction between the hand and box 1? Yeah, sure, because the hand is pushing on it. Is there an interaction between the hand and the table? I don't think so. There's a bit of a gap there, and I don't think there is any interaction. How about box 1 and the table? Sure, for sure. There's going to be the normal force of the table pushing up on the box, and then thus the box pushing down the table, and then there's also the friction. So this is kind of like a double interaction between box 1 and box 2. And how about between the table and box 2? Yeah, I think so. So I think we got everything there. Now it looks a little bit complicated. Yeah, don't worry, but the reason why we did this, it sort of helps us when we draw our force diagrams. So maybe I'll pick some green here and say, okay, so now when I want to draw force diagrams, I can draw a circle around it. Well, which force diagrams am I going to draw? I'm going to draw around box 1. So I think we did this in the past, right, with sort of a line like that. So I'm going to say, okay, I'm going to draw the force diagram for box 1. Oh, I need a little bit more space here, so I'll move it up here. So I'll say box 1. And then I will pick something a bit smaller. Okay, so now each of those red lines should show up in my forces. Okay, so between box 1 and the Earth, well, that's that force of gravity. So on box 1 by the Earth. What's another one? In fact, we can look at the schema or we can look at the picture too, either way. Well, we've also got a normal force of the table. So we can say upwards here, normal force on box 1 by the table. We did say there was going to be friction, and that's another one between the box and the table. If it's moving to the right, then our friction force is going to be to the left. So I'm going to say friction on box 1 by the table. How about the hand? Hand is, I guess we'll call it an applied force, and I think it's pushing it to the right, so we'll do a right force here. Force applied on box 1 by hand. And let's not forget, we have this, the one that we were talking about up over here. We've got that box 2 pushing back on box 1. So we're going to, over here, maybe I'll do this one just a special color here because we want to have it jump out at us. So this would be the well, it's a normal force. Yeah, we already said a normal force on box 1 by box 2. So I just did a different color so it'll pop out at us. All right, now let's think about the fact that this is at constant velocity. So if it's constant velocity, that means that the forces are balanced. So how could we put equality marks? Well, vertically, these two are the only vertical forces, so they're going to balance out. Our horizontal forces are going to balance out too. I don't know, let's try to be original. How about a triangle in this one and a circle in that one, so that this one would be the triangle plus the circle. Does that make sense? Or another way we could say it is that applied force has to be equal to the size of the friction force plus the normal force. Okay, and that's, I'm not thinking about directions, I'm just thinking about the lengths of those arrows. So that, in other words, for it to be balanced, and it's not accelerating. Okay, that looks great. Now let's try box number 2. So I'll say over here somewhere, box 2. And if we do our diagram, I'll do the same. Maybe I'll do it in red again. So similarly, we've got force of gravity downwards. Box 2 looks bigger. Let's assume it's more massive, and then therefore there's more force of gravity acting on it. So I'm going to draw this one a little bit larger here. So force of gravity on box 2 by the Earth. And we're also going to have the table pushing back up on it. So we're going to have this normal force on box 2 by the table. We're going to have, this is my special one here, my normal force of box 1 pushing on box 2. So I'll do this one here, normal force on box 2 by box 1. And well, if it's balanced, what is it that's pushing it to the left? Well, that one is going to be our friction again. So we're going to have this friction force on box 2 by the table. Okay, can we think of some equality marks that we can put on this one? Well, I think that these vertical forces have to cancel each other out, and now the horizontal forces are going to cancel each other out. But instead of just putting, let's see if we can still be consistent with what we put over here. So the other thing that I want to mention is that these two forces we know are also equal. So if I use the circle on that one, I'm going to use the circle on this one, and I'll put a circle on that one. Okay, so there's two thoughts there. The first one is that these two ones, those two forces, are the same interaction. They're going to be equal. So that's why I put the circle there. The reason why I put a circle on the force of friction is because I know that it's moving at a constant velocity, so therefore the forces are balanced. So there's kind of two things I did there. I'm going to stop now and use this example 1, and we'll do example number 2 as another video.